Intro. Welcome back to our channel, where we dive deep into the world of technology and artificial intelligence. Today, we are going to explore an extremely relevant topic in the age of data-driven decision-making: building a seamless AI workflow. Specifically, we'll focus on how to integrate automated data ingestion, model training, and deployment pipelines to create production-ready systems. This is an essential process for organizations looking to harness the power of AI effectively. So, whether you're a data scientist, a machine learning engineer, or just someone curious about AI, stick around as we break down the intricate steps involved in building a robust AI workflow. Section 1: Understanding the AI workflow. Before we get into the nitty-gritty of the integration process, let's take a moment to understand what an AI workflow actually is. Simply put, an AI workflow is a series of processes that enables data scientists and engineers to move from raw data to a trained machine learning model ready for deployment. This process is often broken down into three major components: data ingestion, model training, and deployment. Data ingestion involves gathering data from various sources, which could range from databases to APIs, and sometimes even from real-time data streams. The quality and quantity of this data directly influence the performance of our machine learning models. Model training, on the other hand, is where the magic happens. This is the stage where we take our ingested data and use it to train a machine learning model, allowing it to learn the underlying patterns and make predictions. Finally, we have deployment. This is the stage where the trained model is made available for use in a production environment so that end users can make decisions based on the model's predictions. Each of these components needs to work seamlessly together to create an efficient AI workflow. Section 2: Automated Data Ingestion. Now that we have a foundational understanding of the AI workflow, let's delve deeper into each of the components. We'll start with automated data ingestion. Automated data ingestion is critical because it minimizes the manual effort required to collect data. In today's fast-paced world, data is generated at an astonishing rate, and manual processes simply can't keep up. To automate data ingestion, we can leverage technologies such as Apache Kafka, AWS Kinesis, or even cloud-based ETL, extract, transform, load services. The first step in creating an automated data ingestion pipeline is to identify the various data sources. This might include structured data from relational databases, semi-structured data from APIs, or unstructured data from documents and text files. Once you have identified your sources, you can set up connectors or agents that will continuously pull data from these sources and store them in a centralized data repository. Next, consider the data storage options. You might choose a data warehouse, like Amazon Redshift or Google BigQuery, for structured data, or a data lake solution for unstructured data, such as Amazon S3. The goal is to ensure that the data is easily accessible for the next steps in our AI workflow. It's also essential to implement data validation and cleansing processes at this stage. This could involve checking for missing values, duplicates, and outliers. You might even want to automate these checks using tools like Apache Airflow or Prefect, which are great for orchestrating complex workflows. By implementing these processes early on, we can ensure that the data we feed into our models is high quality and reliable. Section 3: Model Training. Now that we have our data ingested and stored, it's time to move on to model training. The goal here is to create a machine learning model that can learn from the data we've gathered and make robust predictions. First, we need to prepare our data. Data preparation involves feature engineering, which is the process of selecting, modifying, or creating new features from raw data to enhance the model's performance. This could mean normalizing numerical features, encoding categorical variables, or deriving new features through mathematical transformations. The next step is selecting an appropriate machine learning algorithm. This decision is crucial and should be based on the problem you're trying to solve. For example, if you're working on a classification task, you might choose algorithms like logistic regression, random forests, or gradient boosting machines. For regression tasks, algorithms like linear regression or support vector regression might be more suitable. It's often useful to experiment with multiple algorithms to find the one that yields the best performance on your validation dataset. Once you've chosen an algorithm, you'll need to split your data into training and testing sets. A common practice is to use an 80-20 split: 80% of the data for training the model and 20% for testing its performance. This ensures that you can evaluate the model's ability to generalize to unseen data. After training the model, it's crucial to evaluate its performance using appropriate metrics. For classification tasks, you might look at accuracy, precision, recall, and F1 score, while for regression tasks, metrics like RMSE, root mean square error, or MAA, mean absolute error, could be more relevant. In most cases, you'll want to go through a hyperparameter tuning process to optimize your model further. Automated techniques like grid search, random search, or even more advanced approaches like Bayesian optimization can be employed to find the best hyperparameters that improve model performance. Finally, once you're satisfied with your model's performance, it's time to save the model artifacts. This typically includes the trained model itself, along with any necessary metadata. You can store these artifacts in model registries like MLflow or DVC, which help keep track of different versions of your models for future reference. Section 4: Deployment Pipelines. Now that we have a trained model, it's time to deploy it in a production environment. Deployment is a critical step because even the best model in a test environment can fail when it comes to real-world data. The deployment process can be divided into several strategies, including batch deployment and real-time deployment. Batch deployment involves processing data at regular intervals, while real-time deployment allows the model to make predictions on the fly as data comes in. For batch deployment, you can utilize cron jobs or cloud-based scheduling services to run your model at specific intervals. In contrast, for real-time deployment, using REST APIs or streaming platforms like Apache Kafka for serving real-time requests is essential. You'll also need to choose your deployment platform. Options might include cloud services like AWS SageMaker, Google AI Platform, or Azure Machine Learning, all of which provide robust environments for deploying machine learning models. Alternatively, you might host your model on your own servers using frameworks like Flask or FastAPI to create RESTful APIs. One key aspect of deployment is monitoring. Once your model is live, you need to continuously monitor its performance. Metrics like response time, error rates, and the accuracy of predictions should be tracked. Tools like Prometheus or Grafana can help visualize these metrics and alert you if there are any performance drops. Another important aspect is version control. As your model begins to evolve, you'll want to deploy new versions without disrupting the existing system. Techniques like canary deployments or blue-green deployments can facilitate this process, ensuring that the transition to new model versions is smooth and doesn't disrupt service. Section 5: Putting it all together. So, how do we bring all these components together into a seamless AI workflow? The key lies in orchestration and automation. By using workflow orchestration tools like Apache Airflow, Kubeflow, or MLflow, you can create a unified pipeline where each stage of the workflow is automatically triggered based on defined dependencies. For example, after data ingestion is complete, the training process can kick off automatically, and once the model is trained, the deployment stage can follow suit. This continual automation reduces manual intervention and allows for a more agile and responsive system. Moreover, it's essential to foster a culture of collaboration between data engineers, data scientists, and DevOps teams. Communication is key to ensuring that everyone is aligned on the goals and processes involved in the AI workflow. Regular meetings and joint retrospectives can help teams identify bottlenecks and areas for improvement. Finally, remember that building a seamless AI workflow is not a one-time effort. It requires continuous iteration and improvement. Techniques like continuous integration and continuous deployment, CI/CD, for machine learning can help automate the process of updating models and incorporating feedback loops. This ensures that your AI systems remain relevant and effective in a rapidly changing environment. Conclusion. In summary, building a seamless AI workflow involves a systematic approach to automated data ingestion, model training, and deployment pipelines. By integrating these components effectively, organizations can leverage the full power of AI to make data-driven decisions and stay competitive in their industries. Whether you're just starting out or looking to enhance an existing workflow, the principles outlined in today's video will guide you toward creating production-ready AI systems. Don't forget to like, subscribe, and hit that notification bell for more insights into the world of technology and artificial intelligence. Thank you for watching, and we'll see you in the next video.